Okay, so to start off, we're going to review what we did in this problem from last video. We used what we call Hess's law, basically saying that if you add two chemical reactions together, then you also add their delta H's, and the resulting chemical reaction will be that of the delta H. We also saw that we had to do what to solve this problem?
We had to flip the first equation.
That's right. And what happens to the delta H if you flip it?
It changes its sign.
Very good. It changes its sign. And now after we flipped it, then what could we do?
Well, I think you could just add it right to the second equation, right?
Yeah, then we could just add it right to the second equation. And we knew that because they told us the equation we were after. And we looked at these new equations that we had, or this new one here that we got from flipping this first one, and the second one, and we saw that when we added them together and canceled out stuff that was extra, we got our reaction that they wanted to know the delta H of. Okay? So, let's do that same thing with this list of 3 reactions. You know, it's funny, when they give you a list of reactions like this, they really give you a list of 6 reactions. You know why?
No, why?
Well, because you can flip all of these reactions.
Oh, okay, I see what you're saying. But you can also multiply them or divide them by values, right?
What do you mean?
Like the bottom one says H2O liquid goes to hydrogen gas and a half of oxygen gas and requires 285.9 kilojoules.
You were reading this right here?
Yeah. If you multiply that by 2, then that gives you another reaction.
Okay, you're right. You can multiply this by 2 and get another one. You can multiply it by 5, 10, 20, right? You can divide by 1 or 2, divide by 3. So you're right. So when they gave you these 3 reactions, they're not just giving you the 6 of them reversed, they're also giving you lots of different options. Multiplying by values, dividing by values. Okay, good. So keep that in mind as you try to do this one at home. Give it a shot, and then when you're done, come back and Fred will show us how to do it.
I don't think I'm going to be very helpful. You're going to have to help on this one.
Well, we'll do it together then. All right, ready? Hopefully you took a stab at it. Okay, so the chemical reaction that we're after here has C2H2 on the right, and this one has it on the left. So what does that mean?
We probably have to flip it. But I also noticed that it has 2 C2H2s on the left, and we only want 1, and there's no other C2H2s in the other reactions. So we have to flip it and divide by 2.
Okay, so we flip it and multiply by 1/2, which is the same as divide by 2. And how does that change the 2,599.2?
That has to be flip, positive sign, and divided by 2.
Very good. Now, what are we going to do?
Well, the second reaction gives us our carbon, but we need 2, so you're going to have to multiply that one by 2. Don't flip it, though.
All right, so we're not going to flip it, but we do need to multiply it by 2. Now, how did you know that again?
Because it's the only place where we get carbon, and we need carbon, 2 of them in the chemical reaction we're after.
Okay, very good. So, our new delta H is twice as much, not changing the sign, though. Is that right?
Yeah.
Okay, so what about the last one? Is there anything we have to do to the last one?
There's the hydrogen gas, but again, it's on the wrong side, and there's no hydrogen gas anywhere else, so I think we still have to flip it.
Okay, so if we flip it, we just change the sign. We don't change the 285.9, the magnitude. We just change the sign. Now, if I add these 3 blue equations together, am I going to get my reaction?
I think so.
So all the reactants are on the left of these arrows. All the products are on the right. We can see that some things cancel out. Our water cancels out.
Yeah, and then you're just left with the carbon, the hydrogen, and the C2H2. What's C2H2?
That's acetylene. I don't know if you've ever heard of acetylene.
Is that for welding?
Welding. Are you a welder?
Oh, yeah. I'm good with my hands.
Good, good. Okay, so the result then will be the sum of 1299.6, negative 787, negative 787, and negative 285.9, which is our 226.7. Okay, so notice that the state of the compound matters. So if I have this chemical reaction here, C3H8, that's propane. You've heard of propane?
Yeah, I go camping a lot.
Good. Propane combusting with oxygen to form carbon dioxide and water. If the water is gaseous, the chemical process does what? What does this mean?
It means it releases, the negative sign is releases, 2,443 kilojoules.
That's right. Very good. But if it releases the water in the form of liquid, then why is it a different value?
I don't know. Why would that matter?
Well, some of the energy must have gone into the liquid and converted it to a gas. Does that make sense?
Okay, yeah, so it has more energy to release if it doesn't have to convert that liquid to a gas.
Very good. Okay, so there are, it's important to pay attention to the state of your elements or your compounds when you're looking at these chemical reactions. Standard state is something that we use because these statements, like this one here or this one here, are dependent on temperature. They are temperature dependent. And that's because sometimes the product is heat or sometimes the reactant is heat. So if the reactant's heat and you're at a higher temperature, the reaction will be able to proceed better. So these delta H's are dependent on temperature. So we have what's called the standard state. And when we're at standard state, that's at room temperature and pressure. Then we just put a little knot there, or a little circle, which we call it delta H naught. All right? And that means at room temperature, 25 degrees Celsius, 1 atmosphere of pressure. Okay, those are called standard conditions. All right. We also have enthalpy of what we call formation reactions. Formation. We talked about how you can have enthalpy of combustion reactions. Well, enthalpy of formation reactions are very valuable because what they do is they tell us how much energy is kind of stored in a given compound. It's how much energy it takes to create a compound from how the elements are found under natural conditions. So if I want to find out the enthalpy of formation for a compound like calcium carbonate, I just take the calcium, react it with carbon, and react it with oxygen. And I form 1 mole of my species. And that's why you have these fractional coefficients sometimes, because in an enthalpy of formation reaction, you only are forming 1 mole of your material. All right? So the equation that describes the formation of any compound will be an equation that forms that compound from its elements, and it only forms 1 mole of the material. But then if you have a delta H for the formation of a given compound, that's very helpful because you know how much energy is basically stored in those bonds. Now, if it's an element, the delta H of formation will be 0 because the elements, the way they come naturally, you don't gain or lose energy just to get that element, right? So elements, iron comes as a solid iron. Hydrogen comes as hydrogen gas. So we don't get credit for making that hydrogen gas or making the interactions that are occurring in that iron solid, all right? So if I want to know the delta H for a chemical reaction like this, and I have a handy-dandy enthalpy table like this, telling me how much energy is stored in each of these kinds of compounds, I can find the values on this table. So there's negative 285.9 down here, negative 285.9. That's how much energy is stored in the water molecule. Or in other words, if I take hydrogen gas, and I combine it with oxygen gas and form a mole of water, right? So I only need 1 atom of oxygen, so I say 1/2 there. the energy that will be released from that process will be a negative 285.9. Again, if this is a liquid, right? And these are gaseous. So that's how much energy will be stored in that compound. Now it's just 1 mole, so I need to make sure I multiply it by 3 here. But I can do that for all of my products and reactants. And then, again, what this is basically saying is it's saying that if you take all of the elements on the right, iron, oxygen, and hydrogen, and combine them together, this is how much energy will be released. If you take all the elements on the left and combine them together this way, this is how much energy will be released. So if I take the products, the sum of all of these values, negative 822.2, minus the reactants, the sum of all these values, 3 times the negative 285.9, then the products minus the reactants will be the delta H for this reaction. All right? Let's see if you can do the next one here. Folks at home, give it a shot, and then Fred will help us. Okay, Fred, what do you think?
I see carbon dioxide on the list.
Where at? Right here?
Yeah, negative 393.5, and we want 1 mole of it, so just 393. You're good. And then the water, that was, what was it? Negative 285.9, 2 of those.
Very good.
And then on the other side, we have oxygen. Oxygen's element, so 0, right?
That's right. Oxygen is an element, so it's 0. And remember that, because generally they won't give you, this table here gives us all the elements, but generally those won't be provided because they want to know that you know that the delta H of formation for an element, how you find it in nature, is 0, because it's not going to give you any energy to just get that element the way it is. Okay, CH4, how much energy is that?
Let me look. CH4 is negative 74.848.
Very good. Negative 74.848. So, products minus reactants, negative 74.8 minus the sum of all of these is our delta H for our reaction. So, what do you think? Does this process require or release energy?
You mean combining carbon dioxide with water to make oxygen and CH4?
Yeah. Does it require or release energy?
Oh, it's a positive, so it requires energy.
Very good. Requires 890.3 kilojoules to perform this process. All right, one last problem. Why don't you guys try it at home, and then Fred will talk us through it. Okay, what'd you get, Fred?
Well, I have 2 of everything. So, I have to multiply the 691.99 times 2. I have to multiply the negative 285.9 times 2. Add that all together. And then I subtract the negative 699.65 times 2 and the negative 230 times 2.
Very good. And if you do that, what do you get? Does the process require or release energy?
It releases energy. Yeah, negative 96.5 kilojoules.
All right. Very good work.